Yeah, I heard the beep. I'll begin with a word of prayer. So, dear Heavenly Father, we just thank you for this day. Thank you for these students. Just ask you to bless this class this day, Lord. In your name I pray. Amen. So I'm in mourning over something. Nothing to do with the State of the Union. Nothing to do with a test in another class. It's something else. I can't explain, but I feel like something has died, and I have to mourn. So anyway, let us begin over here. Where's my laser? I have no laser. Ooh, here it is. All right. So I like this one. I should just give this problem again and again and again. Then I'd feel like I really taught you guys something because everyone would get it right. So this is right on the money. So we got e to the t plus 3t plus 2t squared. Good to go. That is the dot product indeed. And isn't it amazing that you guys know how to take dot products of functions of time, vector valued functions of time, even though I never defined it? You just did it. Isn't that neat? Because it doesn't need to be defined because you guys have lots of common sense and you don't really need a definition. You already know how to do it. I have at times in the past spent 30 minutes defining it. And students are like, why are you doing this? You know, I'm like, because it's logically necessary. But then I realized it's actually not logically necessary for the audience. Now this right here I like because we've got the 2t minus the 3t squared and the x hat. We've got minus here, and then 2 minus t squared e to the t for the y hat. We've got 3 minus t e to the t for the z hat. That's fine. Then there was this, which might not be as wrong as I thought it was. I'm mostly distracted by the wrongness of this term, but it's, you know, it was for a good cause. It's just that this went askew. Oh, I see. I'm being far too picky here. You just neglected a square here. I was thinking it was something deeper. It's just a typo. Almost exactly right. And I like the way you wrote the answer here. Very nice. Okay, but that's got a square on it still, right? Okay, so that one's good. We take the cross product to get a vector which is perpendicular to two given vectors, right? Which gave, and let's see, is this right? If we take the dot product of 3 minus 2, 2 minus 2 with that, what do we get? 3 plus 2, which is what? 5 minus, 5 minus 4 is 1. Dot product of this and that is not 0. This is wrong. Why is it wrong? It's the same, it's the ever popular, ignore the sign on the middle component error. That's a minus. See, because that's from the y hat, which that minus that. Wait a minute, no, is that what you did? No, it's the first one. Oh, it's the first one. See, I have this bias. I want to see errors in the middle because it's like a, so it's the first one? Oh, I'm sorry, I'm looking at the wrong one. Oh, you're saying that this is just a 2. Oh, okay, yeah. So it's something less exciting. And does that fix it? 2 plus 2, so that ends up being, so 2 plus 2 minus 4 dots to 0. Yeah, that one's perpendicular to both. Okay, we're good. So, yeah, you see, that's why it's so important for you guys to check your, you got to check your answers. It's so easy to make that kind of really silly mistake. And I hate to take points off, but I have to, you know. Now, an add-on to this question might be something like find C1, C2, C3 such that, you know, let's say one, I don't know, let's just keep it simple. 1, 0, 0 is equal to C1 times A, right, plus C2 times B, plus C3 times C. How would you find C1 and C2 and C3? I mean, yes, you could just write it all out and look at 3 equations and 3 unknowns, but I would encourage you for a problem like this, you notice that A, B, and C are what are called orthogonal. If you take the dot product of any 2 of them, it's 0, right? By construction, C is perpendicular to A and B, but A and B I also gave you perpendicular, right? So if I take the dot product of this with A, what do I get? I get C1A dot A. Well, what is A? So A dot x hat is just 1, right? And what's C1? Well, what's A dot A? The length of A squared, right? It's also just by straight computation 2. So I get 2C1, right? C1 equals to 1/2. So maybe that homework question that one of you was asking me, I forgot who. In that problem, are the initial pair of vectors given to be their dot product being 0? I mean, the problem asks you to construct a third vector with length 1 that's perpendicular to the first 2, right? But are the first 2 vectors given in that problem perpendicular?
I think they were.
Because if they are, you can use the strategy to find the constants that I ask you for to build that vector in terms of a combination of the 3 vectors, the 2 which are given, the 1 which you construct.
You don't tell us that they are perpendicular, that A and B are orthogonal to each other, but it's easy to see that they are.
Yeah, yeah. I guess I just told you though.
Well, I wasn't asking about the question, so
I know.
did that one already.
Fine. You stand unhelped.
14.
Let the record state that Nathaniel is helpless. No, no, what's the word? Anyway, I'm sorry. I'll try to stop picking on you. And anyway, you can take the dot product with B and with C to figure out what C2 and C3 are, right? I'm going to stop. That's enough of a hint, I think. Yeah, okay. This one here, this is not quite right. And the reason this is not quite right is I said that this line is tangent to the plane, right? So tangent to the plane means the line looks like this. But this solution assumes that the line is the perpendicular to the plane. That's not what's said here, though. So we want the tangent to the plane. Now, I gave you that there's a point on the plane, right? 1, 0, 0. So that's that line is tangent to the plane. No, it's fine. What's done is done. So this would be fine if I said that was a normal line to the plane. The solution would be legit, right? So how would you go about doing this then? I mean, like, what would you do? Here's what I do. I pick a point on the line. How about t equals 0? That's the laziest thing to do. T equal to 0 gives me 3, 2, 0. Right? What is one vector in the plane already? One vector in the plane already. How about the direction vector of the line? If the line is tangent to the plane, that means the direction vector is in fact a tangent vector. The direction vector here is 1 minus 1, 1. All right? And then I can use, the displacement vector from the base point on the line to the given point on the plane to get another vector on the plane, like so. What's that vector? I'm going to, you can, I think I'm going to, yeah, okay, fine, minus 2, 0, right? And then what I'm after, of course, is the normal vector to the plane, right? So how do I get that? Cross product, right? So, listen, I just want you guys to try something here. You do your best. I'm probably not going to take points off. I just want you to try your best. And like, if I get the sense that everyone's not working, then I will start finding a way to communicate my displeasure and taking off points. But until then, I feel like all you guys are working and things just, sometimes these problems you don't figure out on the fly. Just do your best. It's also instructive for us to see wrong solutions, right? Because I hope that helps you see what not to do also. I think it's helpful to not just see correct solutions. There is value in that. So some of you are like, oh, well then that is a service I can provide. So, right? But I know that's true for me most days, A cross B. Let's see here. So anyway. So we got minus 2, 0, crossed with 1, minus 1, 1. let's see here. Minus 2, let's see here. 2, 4, I think. Now, I could be wrong. Let me just check. Well, it is perpendicular to the second one. And it is perpendicular to the first one. So that'll do it. So that's a normal. Right? Normal to the plane that we're after. And so I know, I mean, you pick your favorite base point, but how about, I'll pick 3, 2, 0 since it's exciting. Minus 2 times x minus 3 plus 2 times x, y minus 2, right? Plus 4z equals to 0. There you go. That's the equation of the plane that has that line tangent to it in that point. Does that make sense? I hope. Maybe. Let's see here. Oh, no. So FA, what this means, and so here, understandably, we haven't talked about this yet, so like it's understandable that you made it into something else, but this is t squared times e to the t, t cubed. So that's scalar multiplication. Scalar multiplication of the function f times the vector a, and that is just equal to, well, I'm going to erase this if no harm, no foul. And so what that is t squared e to the t, and then that's t to the t squared times t cubed, right, which is t to the 5th. So if I wanted to calculate ddt of fa, that would be 2t e to the t plus t squared e to the t, comma 5 t to the 4th. This one over here, we had a miscommunication as to what I meant to start with. So I was trying to communicate sine of t squared, and made it into sine of t squared, which is, a different function. But that's okay. But you changed stream mid-course, which is good. So fine, here's my dA dt, so you use the chain rule and the chain rule here, right? And then dA dt dot a would be this dot that. And I'm just going to go ahead and erase this stuff down here. So what is this actually equal to? Minus 2t. We got sine t squared, right? Cosine t squared plus 2t cosine t squared times the sine of t squared, right? Plus 0. What's this equal to?
Oh my God.
Those are the same thing, right? Yeah. So you're working too hard, man. This is just 0. So this is an interesting vector, interesting path, if you will. I mean, if it is such that the velocity of the path is perpendicular to the position of the path. And then finally over here we have acceleration, t squared, t cubed. I gave that the initial velocity was 1, 1, 1. The initial position was 0, 0, 0. So we can integrate. Yep.
Can I change my answer real quick?
I'll fix it. It's okay. So we integrate. It's funny. We integrate this to get 1/2 t squared, 1/3 t cubed, 1/4 t to the 4th, and plus this. Now, there's some work not shown here. I mean, in principle, you add a constant vector, then you plug in times 0. You find out that times 0 has to be v of 0, which is 1, 1, 1. But you can check it too. If you plug in times 0, what do we get? V of 0 is 1, 1, 1. So it checks with this initial condition. Woohoo! All right. And then to go from here to here, we integrate. So these are good. That's what he wanted to change. These are t's, right? T, t, t. And then in principle, plus some constant vector, right? But that constant vector is actually equal to r of 0, because if you plug in times 0 into this piece over here, everything zeros, right? So whatever the initial position is, it has to be picked up by this constant vector, which we add from the integration, which actually has to be, which is the 0. So in fact, yeah, there it is. That's the position. So, hey, we can solve non-constant acceleration problems in 3 dimensions in like 2 minutes. All we got to do is just integrate twice, right? What's the big fuss about in physics? You spend weeks on this stupid constant acceleration case. I mean, come on, right? Physicists are dumb. Oh, sorry, just kidding. Just things called word problems, and you know, where on earth does this come from, right? Yeah, I mean, if you just focus on the math, it's not that bad. But all right. Excuse me. So let us continue on. So calculus of paths. I just got us started last time. I really need, and you know, there's not too many times in here I really just feel the need to prove things, but this is one of those places where I just really want to prove something for you guys, and I think it's worth a little bit of our time. In particular, these formulas are important. A dot B, all right, this is equal to the sum I equals 1 to n of A sub I, B sub I. This is a nice, slick notation for the dot product. That's just a shorthand for saying, you know, A1, B1 plus dot, 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 plus AN, BN. All right, that's just a shorthand for that. The other shorthand, which is really quite beautiful, is that A cross B. All right, if we look at the kth component of that, A cross B is a vector, right? The kth component of that vector is given by the sum over I and j equals 1 to 3, of course, of what's called the Levi-Civita symbol, epsilon I, j, k, and then you've got yourself an A sub I and a B sub j. What this is nothing more than like epsilon 1, 2, 3, A1, B2, plus epsilon, you know, 2, 1, 3, A2, B1, and so forth. Oh, I'm sorry, the kth component. Where's the k go? K. K. Oh, yeah, that's the thing is I can't do this if I'm going to, that just makes it ugly. I'm sorry. Let me just tell you specifically here. Epsilon 1, 2, 3 equals epsilon 2, 3, 1 equals epsilon 3, 1, 2 is 1. Epsilon 3, 2, 1 equals epsilon 2, 1, 3 equals epsilon 1, 3, 2 equals minus 1. Those are exactly the pluses and the minuses that we put in the cross product. So this is just a slick formula for saying those 6 terms which are non-zero and combine A sub I and B sub j. That's just it's a nice, slick formula for the cross product. So this, again, this thing is the so-called Levi-Civita symbol. I personally learned about this in grad school. So you're like, well, why are you telling us? I don't know. Some of you guys might go to engineering grad school. It's very possible. And I want to do the best I can for you. For the rest of you, relax. Like, I'm not going to test on it. Okay? It is a bonus problem, yeah. That is true. But this is exactly the right kind of notation to prove properties of differentiation for the dot product and cross product. For example, if I wanted to calculate the derivative with respect to time of a dot b, how would I do it? Well, I look at the derivative with respect to time of the sum, k equals 1 to n, of a sub I, a sub I, b sub I, right? What's the derivative of a sum of products of real numbers? I mean, these are just plain old garden variety real functions. I can pull the derivative inside the sum. That's just calc 1. What do I do to a product, though, when I hit it? I just use the ordinary garden variety product rule from calculus 1 on the product of these functions a sub I and b sub I. See, the component of a or b, these are just regular, ordinary, plain old functions. So I can use calculus 1 on those. So here I'm looking at dA di times b sub I plus a sub I times dbi dt. So going from here to here, calc 1, product rule. Rule. I don't know why I'm adding a, sorry. Then you just have to look at this and go, okay, well that can be rewritten as the sum over I of dAi dt bi plus the sum over I of ai dbi dt. All right? But again, I go back to my basic, clean formulas for the dot product and the cross product that I gave you up here, and I just use the dot product formula again, except this isn't the dot product of A and B, it's the dot product of dA dt and B, and this is the dot product of A and dB dt. So this is nothing more than dA dt dot B plus A dot dB dt. What could be more natural? So one of our rules is that if we have the derivative of the dot product of two vector valued functions, we get the following product rule. All right? Through a very similar calculation, I'm going to be, well, what would happen if we tried the cross product? How would this be different with the cross product? What if I erase this dot and make it into a cross? Don't do that in your notes. Make a new thing. I should then add a sub k to it to be fair, right? So what's the formula for that? A little Soprano inspired erasing right there. Ij, epsilon ijk, Dr. Soprano is always erasing with his hand. A sub I, B sub j, if you guys didn't know. Or Dr. Soprano, as you guys often say, but it's actually Soprano. Soprano is something else. Anyway, so there it is. There's the formula for the kth component of the cross product. And then you can just bring, again, if you'll allow me to cheat a little bit here, we could then bring the derivative inside the sum, just like we did before. Right? And here, I'll write the rest of it out. It's almost the same calculation. So this is equal to the sum over I and j of, now I can pull the epsilon ijk outside of the derivative. Why? What's epsilon ijk? It's either 1, minus 1, or 0, depending on your choice of ij and k. It has no time dependence. It's a constant. You can pull it out of the derivative. So all you're really differentiating is the product a sub I and b sub j, which are in principle functions of time. And so what that gives you, of course, is dA dt b sub j plus a sub I dbj dt. And then all I do is I break it up into two sums, and again use this slick formula for the cross product to identify what I have. I'll write one more step out just so you see what I'm doing. So this is just properties of sums. The sum of a sum is the sum of the sums. That makes sense. I guess it didn't seem like I said anything. I'm about to write something though. And so that is nothing more than dA dt cross b, the kth component, plus a cross dB dt, the kth component. That gives me my second rule. I know. I personally find this very reassuring in some sense that there's this natural interplay between the algebra of the dot product and the cross product and this new calculus we're learning of paths. They play together very nicely, and just like you'd expect. So you got to be careful about the order of things, right? Cross products are not commutative, and it matters that you write dA dt first and then b second. And likewise over here, if I switch the order, I can get a minus and it wouldn't be the same, right? But really, if you look at this, what I'm saying is, if you get down into it, it's really just that the product rule gets applied to each component, and that works together with the structure of the cross product to give us this rule. If you do this without the epsilon ijk notation, let me talk about this for a second. You'd have a cross product which has what? 3 components, each one of which has a difference of products. So if you were to differentiate the cross product directly, that is costing you 6 product rules. You then have to take those things and rearrange them and identify that of those 12 terms, 6 of them go into the one cross product and 6 of them go into the other. And that's why I like this notation. So, but I have seen the brute force method is, I mean, it's not impossible to do without this notation. It's just, I prefer the notation. Anyway, enough about the notation. Another thing we could prove is that if we have a scalar multiple of f times a, then this has also got a product rule. It's got df dt times a plus f times dA dt. Look, the derivative, the time derivative of some path, all right, well, the time, you know, what are we differentiating? 1, 2, 3. These are not the same. Which of these is not like the others? Which of these does not belong? I mean, well, I guess it belongs, but which one of these is not like the other? 2 of these are vectors, right? So when we differentiate a vector with respect to time, we differentiate a vector valued function of time, we get another vector valued function of time. So vector in, vector out. Vector in, vector out. Up here, this is a scalar. It's a function of time. Each time you get a number. And over here, this is also a function of time. So there's another rule, which I will not prove. If we have ddt of a of g of t, so here I mean the composition, like you take a vector as a function of time, and then you feed it itself a real valued function of time, then there's a chain rule, and the chain rule is just what you'd expect. It's dA dt of g of t times dg dt. To make that a little less mystical, let me give you an example. If you had a of t, say, equal to cosine of t sinh of t squared, and we had g of t, say, equal to the natural log of t. Then if we differentiate A of g of t, all right, that's going to be dA dt of g of t times dg dt. What does that mean here? What's dA dt? Yeah, thank you, minus sine t, comma, 2t cosh of t squared. And that's with t equal to what? G of t, right? Not the greatest notation. So let me not do this and do it like, instead of putting t there, what should we put? We usually put g, right? So we should put g because we're supposed to evaluate it, the inside function g. And then multiplied by the derivative of g dt, which is, whatever that is. What is g, though? G is natural log t, right? Of course, in detail, that is, well, that's just 1 over t. I'll just leave it out front. And then you've got minus sine of the natural log of t, comma, 2 natural log of t cosh of the natural log of t parentheses squared. Of course, if you just did the composition and differentiated component by component, applying the chain rule in each component, you get the same answer. I just factored the 1 over t out front. And the proof that this rule works the same is just that. You apply the chain rule component by component, and it gives you this. Something more interesting that I should point out to you guys. There's another way of understanding this example. All right? Can you guys tell me what's special about that vector A? What kind of vector is that for each time? It is a unit vector. That is true. So how would we capture something being a unit vector in terms of dot products or cross products? Let's go with dot products. What equation does it mean? I mean, you said it's a unit vector. I agree. The length of A is equal to 1, right? So I hope you guys have picked up on a nice way to analyze such things is to square both sides, right? And so the square of the length is just A dot A, right? A dot A is equal to 1. And this is true for all time. It's true for all time. So these product rules, I mean, you're just itching for an excuse to bring out your silly tensor stuff. It's true. But I'll behave. That won't happen again. There's only really maybe 5 things in the remainder of the course that are kind of proofy that I'll take some time. We do need to prove a couple theorems in here, and I will give you serious proofs of those. But by and large, we just do calculations in here. All right. Anyway, how about we differentiate it? Use the product rule for dot products. What happens when we do that? What happens with ddt of A dot A? Well, it's going to be the derivative of 1. What's the derivative of 1 with respect to time? 0. But on the left-hand side, by our product rule, this is dA dt dot A plus A dot dA dt. But the dot product is commutative. So this gives me that twice A dot dA dt is equal to 0. I think this is a theorem worth remembering. Unit vectors, all right, or, well, to be more honest, unit vector fields. The reason I say it's a unit vector field is Well, I'll shut up. Anyway, definitely a unit vector is going to be perpendicular to its derivative. You see that? So unit vector is perpendicular to its derivative. What's another interesting application for 3? We could look at an application of 3 to kinematics. Actually, this is a combination of different things. We have talked about taking any vector and writing it as a magnitude times a direction, right? So the velocity vector. Suppose v is velocity. We write that as what? We write that as a magnitude times a unit vector, right? So, by the way, the magnitude of v, which we also denote by little v without the vector sign, this is also known as the speed. Right? Speed is the magnitude of the velocity. Okay? And so, we could differentiate this. What happens when we differentiate dv dt? Well, we get ddt of v times v hat, right? Now, v and v hat are both functions of time. One of them is a vector, one of them is a scalar. So we actually use rule number 3 to differentiate, right? Rule number 3 tells me how to differentiate. And so what I get is I get dv dt times v hat plus v times dv hat dt. Of course, this is what? This is acceleration, right? So there's 2 pieces to the acceleration, right? There's the piece that lines up with v hat, and there's the piece which does not. I can draw a picture. I can try to draw a picture. So here's the path we're following, right? So suppose we're at that point at time t. What direction does the velocity go? So we'll soon learn that the velocity points tangent to the graph. Tangent to the path. So here's the velocity direction. Right? The velocity points like that. How about the acceleration? Well, it depends on things I don't have. Yeah, what? Outward. Well, I'm not. There's not enough information here to tell what. You could have this same point set with different accelerations. So until I draw the acceleration vector, it's not really clear. But it has to land on this side, as it happens, for reasons that we'll get into. Acceleration vector looks something like that. There's 2 pieces to it, right? You can look at the orthogonal decomposition of the acceleration into a piece which is tangential and to a piece which is not, which is perpendicular to that tangential direction. The tangential acceleration, oh, there we go again. The tangential piece lines up in the direction of the velocity. It's the part that's the coefficient of v hat. So the tangential piece of the acceleration is something like this guy right here. This is, and I can see it over here. It's dv dt v hat. Sometimes this is called the tangential, piece, tangential component to the acceleration. And then the other piece over here right? Which I'll make. I got a brown here somewhere. Where'd I put it? That's the usual, we call that the centripetal part of the acceleration, right? The center-seeking part of the acceleration. And we have a formula for it here. It's actually equal to the speed times dv hat dt in our current analysis. So the existence of tangential acceleration has to do with the speed changing, right? If the speed is not changing, there's no tangential acceleration. So the case you guys study in Physics 231 the most is constant speed circular motion. Constant speed circular motion only has a centripetal part to the acceleration, right? And you were taught that it's equal to v squared over r. We haven't derived that yet. We will. So, all right, guys, I'm sorry I went over. I will, but I started 2 minutes late, so now we're even, right? Now, tomorrow, arc length. Woo! Oh, and your mission. Turn in and start a class. Yeah. Thanks, guys.